Started the linear discriminant analysis, and we got quite a long way. So that's where we were. So we're in the linear discriminant analysis, we got 2 or maybe more classes, and we're approximating each one by modeling them as if they came from some normal distribution, some multivariate normal distribution with a certain mean and variance. And in the linear discriminant analysis, we're assuming all the variance matrices are the same. And in fact, the right choice is this pooled variance matrix, which is kind of a weighted average of all the variance matrices. Okay. So each individual group is going to be assumed, so it's going to be modeled as if it comes from some multivariate normal distribution with mean equal to the sample group mean. That's to the average of all the observations in that class, and the variance equal to this pooled variance matrix. This gives us a way of allocating new data. So if we get some new data X, we just work out all the probability density functions of each of the classes, and we allocate it to the class where X has the largest or where the probability density function is largest. Okay, so that's the greatest likelihood. Okay, so yeah, and then last time we went on and mostly derived this, and I left the last line or two as an exercise, I guess. I'll write this down on the board. Not because I'm going to do anything with it straight away, but later on we'll see this appear again. So it's our rule is if mu1 minus mu2 dash times sigma inverse x minus mu, which is the mean of mu1 and mu2, should be greater than 0. And in that case, so then we're going to allocate a new reading x to class 1. That's the class that has mean mu1. Okay. So it's a line, if it's in 2 dimensions, that goes through the mean. Mu1 plus mu2 over 2. In 3 dimensions, it's going to be a plane, and in n dimensions, it's going to be some n-1 dimensional thing, which is defined by a linear equation. So that's a hyperplane, but it's always going to pass through this midpoint of the 2 group means. Okay. So that's where we ended yesterday. And in the notes, there may still be a worked example for the iris dataset. Is it still there in the lecture notes? It was there last year. I can't remember if it's still there. Yes. So some people are saying yes, it's still there. Good. I had a sudden fear that I copied some slides from last year and actually changed that part of the notes, and it's no longer true. But anyway, good. Right. So finally, I'll say here that so you can adjust this slightly as a Bayesian version if some groups are more likely to be expected than others. This might happen, for example, if you've got a rare disease that has similar-looking symptoms to a more common one. So remember that we have some that we're kind of motivating this by one probability density function being larger than the other one. So you can kind of imagine that we might have 2 normal distributions like this. If one is much more likely, say, than the other one, so if one is occurring with a certain probability, with say probability pi1 and the other with the probability pi2, what we may do is to weight our graphs and to scale them so that it reflects much more closely the probabilities. And now we're asking instead that the weighted graphs are going to have the appropriate inequality. So here we might be asking that pi 1 times f1 of x is larger than pi 2 f2 of x. And when you go back and do all your earlier calculations about decision boundaries in between two normal distributions, what you find is that you get exactly the same thing. It just it moves your boundary by adding on a constant, so it sort of just shifts it up a bit. And again, you can do the same kind of thing if there are some costs involved. I mean, maybe one diagnosis of, might be a flu and another be polio, and it might be much more expensive if you misdiagnosed polio as flu than the flu is polio, and then you might want to incorporate some extra costs in your model as well, and that works in the same kind of way also. Anyway, to move on then to probabilities of misclassification. So because we're assuming that everything is normally distributed, we can make extra calculations which involve the explicit distribution function of the normal distribution, and we can actually work out how likely it is, if say we're predicting it's in class 1, how likely it is that we're misclassifying it. So we can define our Pij as the probability that an object of type j is misclassified, or just classified as being of the type I. So I should probably say a class J object is classified as being in class I, and we can measure how well our discriminant rulers are doing by working out all these Pij's. And obviously what we really want is that all the Pii's are large, so we're correctly predicting that class I objects are indeed class I, and all the Pij's are small if I and j are different. Okay. And so these Pij's are some kind of an indication as to how well our discriminant rule is performing. Okay. I just said that. Right, so good rules have Pii small and Pij big. Other way around. Yeah, so Pij small for I not equal to j, and Pii big. Yeah, good. We can work out what's going on then for two classes, each being assumed normally distributed. So this is our main calculation here. I'll do some on the board, if I can find a board rubber. There we are. So, let's go back then to our situation where we've got two normal distributions which have a common variance matrix, sigma. And we'll let mu be our midpoint again of our two means. And we can ask ourselves, for any vector alpha, we can project everything onto alpha, and you can ask ourselves, how is alpha dash of x minus mu being distributed? And I rubbed off that thing that I was not intending to rub off. Let's write it again. I'll write it over here. So I wrote down mu1 minus mu2 dash, sigma inverse x minus mu1 plus mu2 over 2, and that thing there is mu, right? So, right, and so you can see that this is alpha dash x minus mu is the kind of an example of this. Right, so if x is in population 1, then its mean is mu1. So x is in the population 1, so it has mean mu1. So x minus mu has mean mu1 minus mu. So mu1 minus mu. So that to mu1 minus a half of mu1 plus mu2, that's just a half of mu1 minus mu2. Okay. So x minus mu then is going to have mean a half mu1 minus mu2. And so alpha dash of this is going to have mean alpha dash times this. So alpha dash x minus mu then is distributed by a normal, a univariate normal distribution with a half alpha dash mu1 minus mu2. Okay, and going back again to what we did earlier about means and variances under projections, the variance of x and the variance of x minus mu are exactly the same, so we're namely sigma, and so the variance of alpha dash x minus mu is alpha dash sigma alpha. Okay. Right. Well, this function here with this with alpha being sigma inverse mu1 minus mu2, this is exactly our discriminant function. Okay, so this is alpha dash here. Okay, so if alpha is sigma inverse times mu1 minus mu2, then the way that matrix multiplication and transposition works tells you that alpha transpose, alpha dash, is the transpose of the second thing, that's mu1 minus mu2 dash, times the transpose of the first thing, and sigma is symmetric, and so its inverses as well. So in fact, here we are working out exactly an instance of alpha dash x minus mu. And so we can actually work out how our discriminant function is distributed. So it's going to be some univariate normal, there's the mean, and there's the variance. Okay. So let's just write down what the mean is. So the mean is going to be a half alpha dash. Well, alpha dash is mu1 minus mu2 dash sigma inverse. That's alpha dash times mu1 minus mu2, that's our mean, where we're using this special value of alpha, which gives us our discriminant rule. And alpha dash sigma alpha, well, alpha dash, we said, was mu1 minus mu2 dash, sigma inverse, and then we're multiplying by sigma, and then alpha is sigma inverse mu1 minus mu2. And you can see here that sigma times its inverse just cancels out. It's just the identity matrix. And so we're getting mu1 minus mu2 dash sigma inverse mu1 minus mu2. That squared Mahalanobis distance between mu1 and mu2. And this is exactly the same thing, except we have a half there. So this is, it tells us then that our discriminant function for x in the group 1 is distributed by this univariate normal distribution with the mean a half for delta squared and variance delta squared. Where delta squared is this squared the Mahalanobis distance. And in exactly the same way, if we assumed that x was in population 2, we'd do exactly the same calculation, except now that if x had mean mu2, we would expect that x minus mu would have for mean say mu2 minus this, which would be a half of mu2 minus mu1, and everything would just get an extra minus sign when we're looking at the mean. Okay, so a discriminant function would be univariate normal with mean minus a half delta squared and variance delta squared. Well, now we can read off our misclassification probability. So let's imagine that x is in population 2. Well, we're going to classify it as being in population 1 if the discriminant function is positive. That's our rule. Okay? So it could be classified as being in population 1 if h of x is positive. And so we're asking for h of x to be positive, but x is in population 2. And there's our distribution of h of x under the assumption that x is in population 2. So we're kind of asking that some normal distribution is taking on some positive value here, and you can just read that off from the distribution of or from the statistics of the normal distribution in terms of that phi function. So it's just minus delta squared over 2 over the square root of the variance. So phi of minus a half delta. And in exactly the same way, you can read off of, the other misclassification probability is exactly the same. So if you've got something in population 1, then the probability that you're going to misclassify it as being in the population 2, it's once again phi of minus a half delta. So in fact, if you've got two normal distributions like this with a common variance, which is what happens in LDA, then you've got two misclassification probabilities, and they're exactly the same. So you can just read them off easily. And of course, then we can actually see what the probabilities of classifying things correctly is. It's just the 1 minus these things. Okay. Right. I think I'll skip over the next a couple of slides, but feel free to verify all the calculations involved. They were very handy for multivariate data analysis in previous years, because I could set lots of nice exam questions involving these, but they're not really so relevant now to machine learning. So the first slide here, it's just asking what happens if you increase the correlation, what happens to the probabilities of misclassification, and it turns out to increase. And when they're uncorrelated, that's the optimal choice that gives you the smallest probabilities of misclassification. And then there's another one which came up on all sorts of old exam papers. If anyone bothers looking at old multivariate papers, I mean, they give sort of random situations where you might be checking two variables, but your equipment breaks and you can only actually check one of them suddenly, or one is really expensive and you can only check one cheaply, and it shows that whenever you've got two variables that gives you more information, it's reducing the probability of misclassifying things than if you're only using one variable. As you'd hope, right? I mean, you've got more information. You'd certainly imagine that that should be helpful and should improve things. Okay. Well, so far I've been talking as if I knew exactly what all the means and the variances were here. So with mu1 and mu2 and sigma, but obviously in the real life we probably don't know that. All we've got is some data points, and so we're estimating our means and our variances. So we're estimating our means by using the normal distributions with mean x1 bar and x2 bar. So they are replacing mu1 and mu2, and we're using our common variance matrix, our pooled variance matrix, which I should probably have called the W, as I did on previous slides as well, and we're using that instead of sigma. Okay. As usual, as I said last week, if you've got new data, then the probability of this classification may be somewhat different. So here we're training our model on existing data, and if we have some new data, then it may do much worse. I mean, maybe this is actually the wrong model, and we're kind of underfitting in some sense. There's a bias because we're using the wrong model, or maybe we're choosing so many parameters that in fact we're overfitting. But that doesn't really happen very often for LDA. But normally you can't really expect that any model is going to do as well on the random data than on the data which it's specifically trained on. Okay, I mean that wouldn't be likely. So if you want some kind of estimate as to how it should do on new data, you should use one of the ideas from chapter 6, say cross-validation or bootstrapping. Okay, so I told you yesterday, and I've previously told you already, that this is not the only way that we can find LDA and motivate it. At least if we got to two classes. So we could instead use a data visualization method and ask, if we project our data onto a single vector, onto a single line, which direction separates things out as highly as possible? So here we're not making any kind of assumption on normality. But we can use this to give some nice graphical displays just by projecting our data. And if you've done lab sheet 4, you'll have seen that already. Or do I mean lab sheet 5? Which one is this one? Lab sheet 5, which you probably haven't done because it's only been up since 12 o'clock. So I'd be very impressive if anyone's done that yet. But so you can see that in fact it produces the graphs much more easily than the PCA does. So where you can really see the groups are separated out. And there's a particularly nice data set on crabs where a plot on the two linear discriminant coordinates, you can really see the four groups really well separated out, and in the PCA that doesn't really happen. If you plot your data on the two principal components, two of the groups are merged and another two groups are merged. Okay. And in exactly the same kind of way as we did in the PCA, we're going to see all this by doing some eigenvector and eigenvalue calculations. It's going to come out again of some Lagrange multiplier process, which I'll do on the board in a minute. And you can see that the directions are, or at least the direction is going to appear magically as the eigenvector of a certain matrix with the largest eigenvalue again. Okay, and then informally at least we can think, and by analogy with the principal components analysis, how about all of the other eigenvectors? Are they somehow useful as well? And those are going to be our higher coordinates. So, as I've already said several times, in LDA we're trying to split out our groups as much as we can. And if we have only two groups, what we're going to see is that the direction of projection is exactly the same as the line that came out of our early analysis, and to this discriminant function here, mu1 minus mu2 dash, sigma inverse x minus mu, is exactly what comes out of this alternative analysis. So what we're going to try and do is to think about the projection. To draw a line. And maybe if I draw a picture, I can go through the slides much more easily. So let's imagine that our two groups are well separated. If we were to project onto some line over here, then everything would be mixed up. I hope you agree. Okay, so let's find some coloured chalk. And use a colour that'll show up nicely on the camera. So we've got one blue group, say, and one red group, and one red group. Then if we project this way, then we're not really going to see any separation at all. That'll be very bad, right? All our entries are going to be projected onto roughly the same line, and we're going to get no separation occurring at all. If we project onto this line, though, so something much nicer will happen. All our red points are going to go into one place, and all our blue points into another one. Okay. And clearly those are much more separated. So what we're going to try and find then is the direction that maximizes the separation, by which I mean it maximizes the between groups variance. So that's the sum of squares as something in the blue group minus something in the red group. Compared with the within groups variance, which is so basically the a sum of squares of one thing in the blue group per minus another thing in the blue group, and one thing in the red group per minus anything else in the red group. Okay. So we're trying to partition our between groups covariance and maximise that and to keep our within groups covariance rather small. Okay. So, unlike a PCA, what we're going to find is that the right direction is an eigenvector of a matrix. Well, I'll tell you the matrix. It'll be W inverse times B, where B is our between groups variance matrix and W is our within groups variance matrix. And so, in particular, W must be invertible. It's a P by P matrix, and it turns out that if you've got n observations, it's only ever invertible if n is actually bigger than the P. So it doesn't work if you've got more variables than observations. Okay. Well, there's our notation from last lecture about the individual group covariance matrices, SI, and the W again is our within groups covariance matrix, and B is our between groups covariance matrix. The W is basically working out the sum of all squares of something in one group per minus something else in the same group, and adding those up and taking some average. And the B is doing the same thing with the one group minus something in a different group, all being squared. As I said yesterday. Okay. So if we project all our data then onto some vector A, exactly like we did in PCA, then if xi dash is our data matrix in the group I, then the projection, that's all the linear combinations, are given by xi dash times A1. Okay, so xi dash is an n by p matrix, or sorry, ni by p, and then we're multiplying by ai, which is a p by 1 vector, or a p by 1 matrix, or a p vector. When we multiply x dash by a1, that means we're taking a linear combination of all the variables of everything in the group I, okay, and finding a single number out for every observation. And then the within group I mean square, that's the sample variance of the group I after projection, is given by A1 dash SI-A1. So that's exactly as we saw earlier on in chapter 1 or 2. Okay, so just a number. And exactly the same way, the within group per mean square of the projected the data is A1 dash WA1, and the projection of the between group per mean square of the projected the data in the same way is A1 dash times B times A1. And what we want is that our groups are widely separated. So really our between groups it should be big, and our within groups should be small. To the idea. So that they should be small. No, that's small and that's big. Okay. And so we can work out this usual F ratio, which is the ratio of the between over within groups of the projections, and that's what we're going to try and maximise. So rather than go through slides, I'll do it on the board again, since I can remind you once again a little bit about how Lagrange multipliers work. So we're trying to choose a vector A1 which maximises this ratio. So maximise F1 here, A1 dash BA1 over A1 dash WA1. Sorry? Are there lights for the board? There are lights on the board. Yeah, as long as it doesn't mess the camera up. There are lights somewhere, probably over here. Yes, that's a good question. So do you think you're in row 1 or row 5? That was the wrong one, wasn't it? Row 5 then. Is that too near? No, that probably makes it worse. Row 4 perhaps. Can you read that? Is that any better? Okay. All right, sorry about that. Right, okay. So this is what we're trying to maximise. So we're going to try and choose a vector A1 that maximises this. Okay. Well, once again, like our PCA calculation, if I scale up A1, so if I double it in the length or something, that leaves this unchanged, right? Because if A1 is doubled in the length, our whole numerator is going to be multiplied by 4, and exactly the same for our denominator. And our ratio is going to be unchanged. Okay, so it's not actually the precise values in A1 that make any difference, just the direction. Okay. So we can always actually insist on some particular scaling of A1. So we're going to scale A1, to leave it unchanged, so that our denominator A1 dash WA1 is 1. So going to leave our F1 unchanged, be exactly the same value, and so then F1 itself is going to simplify a lot, of course. So in fact, we're maximising. We maximise A1 dash times B times A1 subject to A1 dash WA1 equals 1, and then this is our value of F1. Okay. And that should remind you, I hope, of what we did for principal component analysis. So we're going to define a matrix omega, a function omega, which is the thing we're trying to maximize, A1 dash B A1 minus a Lagrange multiplier lambda times our constraint A1 dash WA1 minus 1. Okay, so lambda is our Lagrange multiplier. And we're going to differentiate that with respect to the vector A1. So d omega by dA1, well, our two matrices here, W and B, are both symmetric, and then we can apply our result from chapter 1 that said that when you differentiate, we get 2BA1 minus 2 lambda WA1. So when you differentiate with respect to the vector A1, A1 dash SA1 differentiates to be 2 times S times A1, okay, if S is a symmetric matrix. And so we set this equals 0, and we find that BA1 is lambda WA1, or inverting W if it's invertible, and it may not be. So W inverse B times A1 is lambda A1. And so you can read off that A1 is an eigenvector of the W inverse B. Excellent. So A1 should be this direction. So can we say more? Can we read off what F is? Well, yes. So if I go back here to that line and I multiply by A1 dash, it says that A1 dash BA1 is lambda A1 dash WA1, but A1 dash times WA1 is just 1. So I then find that A1 BA1 is lambda A1 A1 dash WA1, and that's just lambda. So in fact, the lambda then, the eigenvalue, is exactly this value of F1. And that's what we're trying to maximize. So in fact, A1 is going to be the eigenvector which has the largest eigenvalue, just like PCA. Largest eigenvalue. Okay. So it's all working just like PCA did. So in the PCA, it's like we had the variance matrix here and the identity matrix there. But apart from that, it's exactly the same kind of analysis. Right. That probably avoids a few slides. Yeah. Right. Okay. Good. So they've done that, and so this first eigenvector A1. This is the linear discriminant coordinate, or sometimes it's a Fisher's linear discriminant coordinate. Since LDA was invented by Fisher in the late 1930s, I think. So by analogy, with the PCA at least, we can ask about all of the other eigenvectors. How about the eigenvector that has the second largest eigenvalue, and the eigenvector which has the third largest eigenvalue, and so on. And those are known as discriminant coordinates, or sometimes Krim coords, but I hate that word, so I won't use that ever again. And so don't you use it in any assignments or anything. So with discriminant coordinates. And in exactly the same way, you can decompose any data onto these linear discriminant coordinates, and so then you can plot their coefficients. And now normally these axes aren't actually orthogonal, but so nevertheless it still gives you meaningful plots, and you can usually interpret them quite well. And we can't really interpret, we can't really interpret them sort of statistically. I mean, you could try and do it again by analogy as the sort of successive amounts of discrimination, but somehow since things aren't orthogonal, it's not really reasonable. So you have to be rather careful if you do try and interpret things that way. Yeah, and so while I'm here again, you can try and also by analogy with the principal components analysis, you can try and interpret each of the each of the linear discriminant coordinates in terms of the original variables. But here again, unlike a PCA, if you're using the correlation matrix, there's not any normalization process going on here. So it's sort of naturally going to be it's spread out more in the direction where your variables are more spread out. So it's not really reasonable to try and interpret things especially well. So as I say, A1-X is Fisher's linear discriminant function, and the subsequent things are known as discriminant coordinates. And the decision boundaries are given by values of h of x. So it's not really h of x equals naught. That kind of after you've shifted your data. So they're given by values of h of x. Okay. And so A1 is the direction that makes your groups look most distinct in. Okay. Let's end very quickly then by just indicating that if you've got only two groups, then this sort of eigenvector eigenvalue calculation is going to give you exactly the same discriminant function as we found earlier. So when k is 2, it turns out that our between groups variance has a rather simple form. And you can check this by going back to the definition. It's n1 n2 over n times x bar 1 minus x bar 2. That's the mean of all the variables in group 1 and the mean of all the variables in group 2 times the same thing transpose. Now when I transpose so when I multiply a vector by its transpose, I'll get some p by p matrix. So that's just the right. Just if I multiply, say, A B C by A B C.